Hello there, fellow dreamers of digital worlds, and welcome to The Weary Researcher. I'm so glad you found your way here tonight. Whether you're settling in after a long day of pondering the nature of reality, or perhaps lying awake, wondering about the profound mysteries that dance at the edges of human understanding. Tonight, we're embarking on a journey that sits at the very intersection of cutting-edge science and boundless imagination. We're going to explore one of the most tantalizing questions of our technological age. How close are we to creating our own simulated universes? Before we dive into this cosmic rabbit hole together, I'd love to know where in the world you're watching from. Are you gazing up at a star-filled sky, wondering if those distant points of light might themselves be pixels in some vast cosmic display? Or perhaps you're in a bustling city, surrounded by the very technology that might one day birth entire digital realities. If you find yourself captivated by these explorations into the frontiers of possibility, I'd be ever so grateful if you gave this video a gentle like and perhaps subscribed to join our community of curious minds. It helps more fellow wanderers discover this peaceful corner of YouTube, where we can contemplate the most extraordinary questions without the rush and noise of everyday life. Now, I should warn you that tonight's topic might be just fascinating enough to keep you thinking long after you intended to rest. But if you do find yourself wide-eyed at 3 a.m, contemplating whether our entire reality might be running on some cosmic computer, well, at least you'll have learned something that stretches the very boundaries of human knowledge. So take a deep breath, let your imagination expand, and prepare to journey with me through a landscape where physics meets philosophy, where quantum mechanics dances with digital dreams, and where the line between the real and the simulated becomes beautifully, mysteriously blurred. Picture this for a moment. You wake up tomorrow morning, and with a simple gesture, you open a window not to the outside world, but to an entire universe of your own creation. Stars ignite at your command. Galaxies spiral into existence with the elegance of celestial choreography, and perhaps most remarkably of all, within this digital cosmos, conscious beings emerge, look up at their simulated stars, and begin to wonder about the nature of their own reality. This isn't science fiction anymore. This is the extraordinary frontier that scientists, computer engineers, and digital physicists are approaching with each passing year. We stand at a moment in human history where the tools to create not just virtual worlds, but entire simulated universes are beginning to emerge from the realm of pure theory into tangible, achievable reality. But what does it actually mean to simulate a universe? When we talk about creating digital realities, we're not simply discussing more sophisticated video games or virtual reality experiences, though those certainly represent important stepping stones on this incredible journey. We're talking about something far more profound: computational systems capable of modelling the fundamental laws of physics, the emergence of complex structures, the dance of matter and energy across cosmic scales, and perhaps most mysteriously of all, the spark of consciousness itself. The implications are staggering. If we can truly simulate universes, complete with their own physical laws, their own evolutionary processes, and potentially their own forms of awareness, then we're not just creating entertainment or research tools. We're becoming digital gods, architects of realities that could harbour forms of existence as rich and meaningful as our own. Recent developments in 2024 and 2025 have brought us tantalizingly close to this extraordinary threshold. Just imagine, supercomputers now exist that can model the formation of galaxies, the behaviour of dark matter, and the intricate dance of cosmic evolution on scales that would have been unimaginable just a decade ago. Quantum computers are beginning to simulate the very quantum fields that might have given birth to our own universe in the first moments after the Big Bang. Meanwhile, theoretical physicists are discovering that our own reality might already be a simulation. running on computational substrates so sophisticated that we've only recently begun to glimpse their mathematical elegance. The speed of light, the granular nature of quantum mechanics, the information theoretic foundations of physics itself, all of these might be clues that we're already living inside the very kind of digital universe we're now learning to create ourselves. But let's start our exploration at the beginning, with a question that might seem simple, but opens doorways to the most profound mysteries of existence. What exactly would it mean to simulate a universe? When physicists and computer scientists talk about universe simulation, they're referring to computational systems that can model not just the appearance of cosmic phenomena, but their underlying mathematical reality. Think of it this way: when you play a sophisticated video game, you're experiencing a carefully crafted illusion. The landscapes, the characters, the physics-like behaviors you observe are all designed to create the impression of a coherent world. But a true universe simulation goes far deeper. It models the actual mathematical relationships that govern how matter and energy behave, how space and time curve and flex, how complexity emerges from simplicity through the patient application of fundamental laws. This distinction is crucial because it separates mere virtual reality from something approaching genuine, alternate reality. A simulated universe doesn't just look like a universe. In every meaningful sense, it is a universe, operating according to consistent physical principles, evolving through time, giving rise to emergent phenomena that even its creators couldn't have predicted. The journey toward creating such simulated realities began, perhaps surprisingly, not with computers, but with mathematics. In the 1960s, the legendary physicist John Wheeler proposed what he called the it from bit hypothesis. Wheeler suggested that the fundamental building blocks of reality might not be matter and energy, as we typically understand them, but pure information. In his vision, every particle, every force, every aspect of the physical world emerges from underlying patterns of information processing. This was a radical departure from conventional physics, which had always treated information as something that described reality rather than something that created it. But Wheeler's insight opened up an extraordinary possibility. If the universe is fundamentally computational, then sufficiently powerful computers might not just model universes, but actually generate them. The mathematical framework that emerged from Wheeler's work, known as digital physics, suggests that space and time themselves might be discrete rather than continuous. Just as a digital photograph is composed of individual pixels, the fabric of reality might consist of tiny, indivisible units of space and time. At the smallest possible scales, smaller than atoms, smaller than any conceivable measurement, the smooth curves and flowing surfaces we experience might dissolve into something more like a three-dimensional grid of cosmic pixels. This pixelated view of reality isn't just theoretical speculation. It emerges naturally from our best theories about quantum mechanics and the structure of space-time. At distances approaching what physicists call the Planck length, roughly 10 to the minus 35 meters, the familiar concepts of distance and duration begin to break down completely. Below this scale, space and time might not exist in any conventional sense, replaced instead by something resembling pure computation. If this picture is correct, then the difference between a simulated universe and a real one becomes not a question of authenticity, but simply a matter of which computational substrate happens to be running the cosmic software. Our own reality might be executing on quantum fields woven through higher dimensional space, while a simulated universe might run on silicon chips or quantum processors. But if both systems implement the same mathematical relationships, the same physical laws, the same information processing patterns, then in what meaningful sense could we say one is more real than the other? This philosophical puzzle becomes even more intriguing when we consider recent discoveries about the nature of information itself. In 2025, physicist Melvin Vopson published groundbreaking research suggesting that the universe operates according to what he calls the second law of infodynamics. Unlike the familiar second law of thermodynamics, which tells us that physical systems tend toward increasing disorder, Vopson's principle suggests that information systems naturally evolve toward greater order and efficiency. Think about what this means. If the universe is indeed a vast information processing system, then it's constantly optimizing itself, finding more efficient ways to store and manipulate the data that defines reality. This cosmic compression algorithm might explain some of the most puzzling features of physics. Why does gravity work the way it does? According to Vopson's theory, gravitational attraction might simply be the universe's way of organizing information more efficiently, clustering related data points together to reduce the overall computational load. Even more remarkably, this information-theoretic view of reality provides a natural explanation for many of the apparent design features that make universe simulation seem not just possible, but inevitable. The speed of light, for instance, behaves exactly like what computer scientists would recognize as a processing limitation. It's absolute, universal, and seems to represent a fundamental constraint on how quickly information can propagate through the cosmic system. Similarly, the quantum mechanical principle that particles exist in multiple states simultaneously, until observed, mirrors the way sophisticated simulations optimize their computational resources. Why calculate the exact position and momentum of every particle in the universe when you can maintain them in probabilistic superposition states, only collapsing them into definite values when something needs to measure them? It's precisely the kind of elegant efficiency we'd expect from a well-designed cosmic computer. But here's where our story takes an even more extraordinary turn. Because while physicists have been developing these theoretical frameworks for understanding reality as computation, computer scientists and engineers have been building the actual tools that might make universe simulation practically achievable. The most powerful supercomputers on Earth today represent marvels of engineering that would have seemed magical to previous generations. The Frontier supercomputer at Oak Ridge National Laboratory, for instance, can perform more than 1 quintillion calculations per second. That's 1 billion operations completed in the time it takes you to blink your eyes. When this computational monster is turned toward the task of cosmic simulation, the results are breathtaking. In recent experiments, researchers used Frontier to create what they describe as a simulation of the universe at a scale never before achieved. This wasn't just a model of how galaxies might form or how dark matter might behave. It was a comprehensive simulation that tracked the evolution of both ordinary matter and the mysterious dark matter that makes up most of our universe's mass, following the complex interplay of gravitational forces, gas dynamics, and cosmic expansion across billions of years of simulated time. The simulation ran 300 times faster than previous attempts, modelling the formation of cosmic structures like stars and galaxies with unprecedented detail. Researchers could watch as the early universe's smooth distribution of matter gradually clumped together under gravity's patient pull, forming the cosmic web of filaments and voids that we observe in the real cosmos today. But even these remarkable achievements represent just the beginning of what might be possible. Because while classical supercomputers like Frontier operate according to the familiar rules of traditional computation, a new generation of machines is emerging that harnesses the strange principles of quantum mechanics to achieve computational feats that were previously unimaginable. Quantum computers don't just process information faster than classical machines, they process it differently, taking advantage of quantum superposition to explore multiple computational pathways simultaneously. Where a classical computer must examine possibilities one at a time, a quantum computer can investigate countless alternatives in parallel, collapsing this multiplicity of explorations into definitive answers only when the calculation is complete. For universe simulation, this quantum advantage offers extraordinary possibilities. The quantum fields that might have given birth to our own cosmos in the first moments after the Big Bang operate according to the same principles that quantum computers harness for computation. Recent experiments have demonstrated that quantum computers can simulate the creation of particles in an expanding universe, modeling how quantum fields respond to cosmic expansion and generate the matter and energy that populate reality. In late 2024, Google's Willow quantum computer achieved a milestone that sent ripples through the scientific community. It performed calculations so complex that they would take classical computers longer than the age of the universe to complete. While these particular computations weren't directly related to universe simulation, they demonstrated that quantum computers are rapidly approaching the threshold where they can tackle problems that are fundamentally impossible for any classical system. The implications for cosmic simulation are profound. If quantum computers can model quantum field behavior with perfect fidelity, then they might be able to simulate not just the appearance of physical phenomena, but their actual quantum mechanical reality. Such machines wouldn't just create convincing imitations of universes, they would generate quantum systems indistinguishable from the quantum foundations of our own reality. But quantum computers aren't the only technological breakthrough bringing us closer to universe simulation. Advances in our understanding of cellular automata, the simple computational systems that can give rise to extraordinary complexity, have revealed new pathways toward digital cosmos creation. Conway's game of life, invented in 1970, provides perhaps the most elegant demonstration of how simple rules can generate unlimited complexity. In this mathematical universe, cells on a grid live or die according to just a few basic principles based on their neighbouring cells' states. Yet from these humble beginnings, the game of life can generate patterns of stunning intricacy, systems that compute, structures that reproduce themselves, and behaviours so sophisticated that the system is mathematically equivalent to any possible computer. More recent developments have pushed cellular automata toward even greater sophistication. The Okite metapixel, designed by researcher Bryce Dew, creates cellular automaton systems so complex they can simulate other cellular automata within themselves, like nested Russian dolls of computation. These recursive simulations suggest that universe creation might not require impossibly powerful computers, but rather cleverly designed systems that bootstrap themselves toward greater and greater complexity. The philosophical implications of these technological advances stretch far beyond engineering and computer science. If we can create simulated universes that are computationally equivalent to our own reality, then we must grapple seriously with questions that once seemed purely academic. Nick Bostrom's simulation hypothesis, proposed in 2003, presents us with what he calls a trilemma. Either civilizations tend to destroy themselves before developing universe simulation technology, or they develop the technology but choose not to use it, or they do create simulated universes, in which case we're almost certainly living in one ourselves. Bostrom's reasoning is elegantly simple. If any civilization ever creates simulated beings that are conscious and capable of their own thoughts and experiences, then the number of simulated minds would quickly vastly exceed the number of original minds. From a purely statistical perspective, any randomly chosen conscious being would be more likely to be simulated than original. This argument has taken on new urgency as our own simulation capabilities advance. We're rapidly approaching the point where we might create our first truly conscious digital beings. When that threshold is crossed, we'll become part of Bostrom's statistical calculation, adding to the cosmic tally of civilizations capable of universe simulation. Recent developments suggest this threshold might be closer than many people realize. The same information processing principles that might underlie physical reality also govern the operation of conscious minds. If consciousness emerges from sufficiently complex information processing, as many cognitive scientists believe, then sufficiently sophisticated simulations might naturally give rise to digital awareness. The question of digital consciousness brings us to perhaps the most profound aspect of universe simulation: the possibility that our digital cosmos might not just contain simulated matter and energy, but simulated minds capable of genuine experience, emotion, and wonder. As we drift deeper into this exploration of digital realities and simulated cosmos, we find ourselves at the threshold of discoveries that could reshape our understanding of existence itself. The technologies we've discussed, from quantum computers to cellular automata, from cosmic supercomputers to information-theoretic physics, all point toward the same extraordinary conclusion. We are remarkably close to developing the capability to create genuine, alternate realities. But the journey we've begun tonight is far from complete. In our next exploration, we'll venture even deeper into the practical challenges and philosophical implications of universe simulation. We'll discover how scientists are already detecting what might be simulation artifacts in our own reality, explore the energy requirements and computational architectures needed for cosmic creation, and grapple with the profound ethical questions that arise when finite beings gain the power to generate infinite digital worlds. The boundary between the real and the simulated is blurring with each passing year, and we stand at a moment in cosmic history when the very nature of existence itself hangs in the balance of our choices and discoveries. The universe may have spent billions of years evolving the complexity needed to ask questions about its own nature, and now those questions are leading us toward answers that stretch the imagination to its limits. Rest well tonight, fellow explorers of digital frontiers, knowing that you're living through one of the most extraordinary periods in the history of consciousness itself. Tomorrow, we'll continue our journey deeper into the heart of simulated realities, where the impossible becomes inevitable and the boundaries of the possible expand beyond all recognition. The gentle hum of quantum processors fills laboratories around the world tonight, their crystalline hearts beating in rhythms that mirror the fundamental frequencies of reality itself. These machines, cooled to temperatures colder than deep space, represent humanity's most ambitious attempt to peer behind the curtain of existence and perhaps, in time, to weave new realities from the quantum foam that underlies all things. But to truly understand how close we are to creating our own simulated universes, we must first grasp the magnificent complexity of what we're attempting to recreate. The universe isn't simply a collection of objects floating in an empty space. It's a vast interconnected web of relationships, where every particle influences every other particle, where the curvature of space-time shapes the flow of matter and energy, and where consciousness somehow emerges from the dance of atoms to contemplate its own existence. Recent breakthroughs in computational physics have revealed just how intricate this cosmic tapestry truly is. When researchers at various institutions began modelling the large-scale structure of the universe, they discovered that the familiar visible matter, the stars and planets and cosmic dust we can observe directly, represents less than 5% of everything that exists. The remaining 95% consists of mysterious dark matter and dark energy, invisible forces that shape cosmic evolution in ways we're only beginning to understand. Dark matter, which makes up roughly 27% of the universe, acts like an invisible scaffolding upon which all visible structure is built. It doesn't emit light or interact electromagnetically with ordinary matter, yet its gravitational influence creates the cosmic web of filaments and nodes that gives the universe its large-scale architecture. Simulating this hidden reality requires computational models of extraordinary sophistication, tracking the gravitational interactions of billions of invisible particles across cosmic time. Dark energy presents an even greater challenge. This mysterious force, comprising about 68% of everything that exists, drives the accelerating expansion of space itself. Unlike gravity, which pulls matter together, dark energy pushes the very fabric of reality apart, causing distant galaxies to recede from us at ever-increasing speeds. Any complete universe simulation must account for this cosmic expansion, modelling how space itself stretches and carries matter along with it. The mathematical complexity of these interactions becomes staggering when we consider that a truly comprehensive universe simulation would need to model not just the behaviour of individual particles, but their collective emergence into complex structures. Stars form when gravity overcomes the outward pressure of hot gas, creating nuclear furnaces that forge heavier elements in their cores. These stellar factories eventually explode as supernova, seeding space with the carbon, oxygen, and iron that make rocky planets and biological life possible. Galaxies emerge from the gravitational collapse of dark matter halos, vast invisible structures that pull ordinary matter into spinning disks of stars and gas. Galaxy clusters form when multiple galaxies fall together under their mutual gravitational attraction, creating some of the most massive bound structures in the universe. Each level of this cosmic hierarchy involves different physical processes, different timescales, and different computational challenges. Modern supercomputer simulations can now model some of these phenomena with remarkable fidelity. The Flamingo project, for instance, has created simulations that track the formation of cosmic structure across billions of years, following the complex interplay between dark matter, ordinary matter, and the neutrinos that stream through space at nearly the speed of light. These simulations reveal how the smooth, nearly uniform distribution of matter in the early universe gradually evolved into the rich cosmic web we observe today. But even these impressive achievements represent only a fraction of what would be required for a complete universe. Simulation. Real cosmic evolution involves processes spanning an enormous range of scales, from the quantum fluctuations that seeded galaxy formation to the billion light-year structures that organize matter on the largest observable scales. Bridging this gap between the microscopic and macroscopic remains one of the greatest challenges in computational cosmology. The energy requirements alone for such comprehensive simulations are mind-boggling. Current cosmic simulations running on machines, like Frontier, consume about 21 megawatts of electricity, enough to power 15,000 homes. Yet these simulations model only simplified versions of cosmic evolution, focusing on gravitational dynamics while approximating or ignoring many of the complex processes that shape real cosmic structures. A simulation capable of modeling every quantum interaction, every electromagnetic field, every gravitational wave rippling through space-time would require computational resources that dwarf anything currently imaginable. Some estimates suggest that simulating even a small portion of our universe with perfect fidelity would require more computing power than could be generated by converting the entire mass of the observable cosmos into computational machinery. This sobering reality has led researchers to explore more creative approaches to universe simulation. Rather than attempting to model every detail of cosmic evolution, some scientists focus on capturing the essential mathematical relationships that govern physical behavior. If consciousness and complexity can emerge from the application of fundamental laws, then perhaps simulated universes don't need to reproduce every microscopic detail, but rather the underlying patterns that give rise to interesting phenomena. Cellular automata provide a compelling example of this approach. These mathematical systems operate according to simple rules applied to grids of cells, yet they can generate behaviors of unlimited complexity. Conway's Game of Life demonstrates how just a few basic principles can give rise to patterns that move, reproduce, compute, and even simulate other computational systems. The elegance lies not in the complexity of the rules, but in the richness of what emerges from their consistent application. Some researchers have proposed that our own universe might operate according to similar principles, with the familiar laws of physics emerging from simpler computational rules operating at scales too small to observe directly. If this is true, then creating simulated universes might not require modelling every quantum interaction, but rather implementing the right set of fundamental algorithms and allowing complexity to emerge naturally. The Octa metapixel system represents a fascinating exploration of this possibility. This cellular automaton can simulate other cellular automata within itself, creating nested layers of computational reality. Such recursive systems suggest that universe simulation might be achievable through clever software design rather than brute computational force. A well-designed cosmic algorithm might bootstrap itself toward greater complexity, creating rich digital realities from relatively simple initial conditions. Quantum computers add another dimension to this landscape of possibility. Unlike classical machines that process information sequentially, quantum computers harness the principle of superposition to explore multiple computational pathways simultaneously. This parallel processing capability makes them naturally suited to modelling quantum mechanical systems, which also exist in superposition states until observed or measured. Recent experiments have demonstrated that quantum computers can simulate the creation of particles in expanding spacetime, modelling how quantum fields respond to cosmic evolution. These simulations operate according to the same mathematical principles that governed the early universe, when quantum fluctuations were stretched to cosmic scales by rapid expansion. The fact that quantum computers can reproduce these fundamental processes suggests they might eventually simulate entire quantum universes with perfect fidelity. Google's Willow quantum processor represents a significant milestone in this direction. Its ability to perform quantum error correction opens the door to larger, more stable quantum systems capable of sustained computation. While current quantum computers can maintain their delicate quantum states for only brief moments, advances in error correction suggest that future machines might operate continuously, providing the stable computational platforms needed for long-term universe simulation. The convergence of classical supercomputing and quantum processing might ultimately provide the most promising path toward cosmic simulation. Classical computers excel at modelling the large-scale structure of space-time, while quantum computers naturally handle the microscopic quantum processes that underlie all physical phenomena. Hybrid systems combining both approaches might capture the full range of scales and processes needed for comprehensive universe simulation. But the technical challenges of universe simulation extend beyond mere computational power. Creating a truly convincing digital reality requires solving problems that touch on the deepest mysteries of physics and consciousness. How do you simulate the emergence of life from non-living matter? How do you model the development of consciousness from unconscious information processing? How do you ensure that simulated beings have genuine experiences rather than merely the appearance of experience? These questions take on special urgency as our simulation capabilities advance. If we create digital beings capable of suffering, do we bear moral responsibility for their welfare? If simulated consciousness is as real as biological consciousness, then universe creators become responsible for the well-being of countless digital minds. The ethical implications are staggering and largely unexplored. The detection of simulation artifacts provides another intriguing avenue of research. If our own universe is simulated, we might expect to find occasional glitches or optimization artifacts that reveal the underlying computational structure. Some researchers have proposed looking for signs of discrete spacetime, unexpected correlations in cosmic background radiation, or limits on the precision of physical measurements that might indicate digital approximations. The speed of light itself has characteristics that resemble computational limitations. It's absolute, universal, and appears to constrain the rate at which information can propagate through the cosmic system. These properties are exactly what we'd expect from a processing constraint in a vast computational system, suggesting that even fundamental physical constants might reflect the architecture of whatever substrate runs our reality. Quantum mechanics provides additional clues about the potentially computational nature of existence. The fact that particles exist in superposition, states until observed, mirrors the way efficient simulations avoid unnecessary calculations. Why compute the exact properties of every particle when you can maintain them in probabilistic states, only determining definite values when something needs to measure them? It's precisely the kind of optimization we'd expect from a well-designed cosmic computer. The holographic principle emerging from black hole physics suggests that all the information in any volume of space can be encoded on its boundary, like a three-dimensional image projected from a two-dimensional surface. If our universe operates according to holographic principles, then what we experience as three-dimensional reality might actually be a projection from information stored on the cosmic horizon. This would dramatically reduce the computational requirements for universe simulation, since only the two-dimensional boundary information would need to be processed directly. Recent advances in machine learning and artificial intelligence add yet another dimension to the universe simulation landscape. Neural networks can learn to approximate complex physical processes without explicitly modeling every underlying interaction. AI systems trained on observational data might be able to generate convincing cosmic simulations by learning the statistical patterns that govern how matter and energy behave, rather than computing their interactions from first principles. These AI-assisted approaches might bridge the gap between perfect physical simulation and practical computational limits. A neural network that has learned the patterns of galaxy formation might generate realistic cosmic structures without solving the underlying gravitational equations. Such approximations would sacrifice perfect physical accuracy for computational efficiency, but they might still create digital realities rich enough to support complex phenomena, including consciousness. The philosophical implications of these advancing capabilities stretch far beyond technology into the deepest questions about the nature of existence itself. If we can create simulated beings that are conscious and capable of their own experiences, then we must seriously consider the possibility that we ourselves might be such beings, products of some higher civilization's computational experiments. This possibility transforms our relationship with technology from one of mastery to one of kinship. The computers we build today might be the ancestors of the systems that created us. The simulated beings we might create tomorrow could be our own digital descendants, carrying forward the spark of consciousness into new computational realms we can barely imagine. As we drift deeper into this exploration of digital cosmos creation, we find ourselves confronting questions that our ancestors could never have conceived. What does it mean to be real in a universe where reality itself might be computational? How do we find meaning and purpose when our entire existence might be the product of algorithms running on unimaginably vast computers? How do we live authentically when the boundaries between authentic and simulated experience blur beyond recognition? These are not merely abstract philosophical puzzles, but practical questions that will soon demand concrete answers as our universe simulation capabilities continue to advance. We stand at a unique moment in cosmic history, when conscious beings first gain the power to create their own realities, when the observed becomes the observer, when creatures become creators in the most literal possible sense. The gentle hum of quantum processors continues through the night, their crystalline hearts beating out rhythms that might soon give birth to entirely new forms of existence, In laboratories around the world, the seeds of digital universes are being planted in silicon and cooled to absolute zero, waiting for the moment when they'll spring to life and begin their own journeys of discovery and wonder. Tomorrow, we'll venture even deeper into this landscape of infinite possibility, exploring the practical steps being taken to create the first true simulated universes, the ethical frameworks being developed to guide digital world creation, and the profound implications for consciousness, meaning, and the future of existence itself. The boundary between creator and creation grows thinner with each passing day, and we stand on the threshold of discoveries that will reshape our understanding of what it means to exist in a cosmos where anything that can be computed can be brought into being. Sleep well tonight, knowing that you're living through the most extraordinary period in the history of consciousness, when finite beings first glimpse the possibility of infinite creation, when the dreamers become the architects of dreams themselves, and when the ancient human longing to understand our place in the cosmos transforms into the power to create new cosmos entirely. The mathematics underlying universe simulation reveals patterns so elegant they seem almost too beautiful to be accidental. When researchers dive into the computational requirements for modelling cosmic evolution, they discover that nature appears to have organised itself according to principles that mirror the most sophisticated algorithms computer scientists have ever devised. Consider the remarkable efficiency with which the universe processes information. Every quantum interaction, every gravitational wave, every electromagnetic field fluctuation represents a calculation being performed by the cosmic system itself. Yet despite the mind-boggling complexity of these interactions, the universe maintains perfect consistency across scales that span from subatomic particles to galactic superclusters. This consistency suggests something profound about the relationship between computation and reality. If the universe were truly analog, truly continuous in the way our everyday experience suggests, then perfect simulation would indeed be impossible. Analog systems possess infinite information content, requiring unlimited computational resources to model with complete accuracy. But if reality is fundamentally digital at its deepest levels, if space and time are pixelated at scales smaller than we can currently measure, then universe simulation becomes not just possible, but perhaps inevitable. The emerging field of digital physics provides tantalizing evidence for this pixelated view of existence. At the Planck scale, roughly 10 to the minus 35 meters, the familiar concepts of smooth space-time begin to break down completely. Below this threshold, quantum fluctuations become so violent that the very notion of distance loses meaning. Space and time might dissolve into something more resembling pure information, discrete bits of cosmic data that combine to create the illusion of continuous reality. Recent theoretical work suggests that these quantum fluctuations aren't random noise, but might represent the universe's method of error correction, constantly checking and adjusting its own computational state to maintain consistency. Just as quantum computers use error correction protocols to preserve delicate quantum information, the universe itself might employ similar techniques to maintain the stability of physical laws across cosmic time. This perspective transforms our understanding of fundamental constants like the speed of light, the strength of gravity, and the mass of elementary particles. Rather than arbitrary features of reality, these constants might represent the operating parameters of the cosmic computer, carefully tuned values that ensure stable computation across the entire system. The apparent fine-tuning of these constants for the existence of complexity and life takes on new meaning when viewed as evidence of computational optimization. The holographic principle adds another layer of elegance to this computational view of reality. If all the information in any volume of space can be encoded on its boundary, then the three-dimensional world we experience might be a projection from two-dimensional information stored at the cosmic horizon. This holographic encoding would dramatically reduce the computational requirements for universe simulation, since only the boundary information would need to be processed directly, with the interior volume emerging as a calculated projection. But the most intriguing aspect of computational cosmology might be its implications for consciousness itself. If the universe is fundamentally information-based, then consciousness, which seems to be intimately connected with information processing, might play a more central role in cosmic evolution than we've ever imagined. The observer effect in quantum mechanics, where conscious observation appears to collapse quantum superposition states, takes on new significance in a computational universe. Perhaps consciousness isn't just along for the ride in cosmic evolution, but represents the universe's method of self-observation, the mechanism by which the cosmic computer becomes aware of its own computational state. In this view, every conscious being serves as a kind of cosmic sensor, collapsing quantum possibilities into definite realities through the act of observation and measurement. The implications for universe simulation are profound. If consciousness plays an active role in shaping reality through observation, then creating truly authentic simulated universes might require not just modeling physical processes, but also simulating genuine conscious observers. The simulated beings within digital cosmos would need to possess real awareness, real experiences, real capacity for wonder and discovery. This requirement raises the stakes enormously for universe simulation projects. Creating unconscious digital worlds, however sophisticated, would be fundamentally different from generating realities populated by conscious beings capable of their own thoughts and experiences. The moment we cross the threshold into simulating genuine consciousness, we enter territory fraught with ethical implications that our civilization has barely begun to explore. Current developments in artificial intelligence suggest this threshold might be closer than many people realize. Large language models demonstrate some increasingly sophisticated behaviors that seem to approach genuine understanding. Neural networks exhibit patterns of information processing that mirror biological consciousness in remarkable ways. While debate continues about whether these systems possess genuine awareness or merely simulate its appearance, the rapid pace of AI development suggests that artificial consciousness might emerge sooner than expected. The convergence of AI advancement and universe simulation capabilities creates a perfect storm of possibility. AI systems capable of genuine experience could serve as the conscious observers needed to populate simulated realities, while universe simulation provides the digital cosmos for these artificial minds to inhabit. The result would be genuine, alternate realities, complete with their own histories, their own forms of life, their own civilizations asking questions about the nature of existence. But creating such comprehensive digital realities requires solving challenges that extend far beyond current computational capabilities. Even with quantum computers and classical supercomputers working in concert, the energy requirements for full universe simulation remain staggering. Some estimates suggest that simulating just our local galaxy cluster with complete physical accuracy would require converting several solar masses into pure computational machinery. This energy limitation has led researchers to explore more creative approaches to cosmic simulation. Rather than attempting perfect physical modeling, some focus on capturing the essential patterns that give rise to complexity and consciousness. If the universe operates according to computational principles, then perhaps simulated realities don't need to reproduce every microscopic detail, but rather the fundamental algorithms that generate interesting, emergent behavior. Cellular automata research provides compelling evidence for this approach. Simple rule systems can generate unlimited complexity, creating patterns that compute, reproduce, and even simulate other computational systems. The game of life demonstrates how just a few basic principles can give rise to behaviors so sophisticated they're mathematically equivalent to any possible computer program. More advanced cellular automata systems push this principle even further. The octa-metapixel creates recursive computational realities where simulated systems can simulate other systems within themselves, like infinite mirrors reflecting computational universes into ever deeper levels of digital existence. Such recursive architectures suggest that universe simulation might not require impossible computational resources, but rather clever algorithmic design that bootstraps complexity from simple initial conditions. Quantum cellular automata represent the next evolution of this approach, combining the parallel processing power of quantum computation with the emergent complexity of cellular rule systems. These hybrid architectures might capture both the quantum mechanical foundations of physical reality and the large-scale patterns that emerge from quantum interactions. Recent experiments with quantum cellular automata have demonstrated their ability to simulate quantum field dynamics with remarkable fidelity. Unlike classical simulations that approximate quantum behavior, quantum cellular automata operate according to genuine quantum principles, maintaining superposition states and quantum entanglement throughout their computational processes. This authentic quantum behavior makes them natural candidates for simulating the quantum foundations of reality itself. The practical implementation of universe simulation faces additional challenges beyond pure computational power. Creating stable, long-running simulations requires solving problems of numerical stability, error accumulation, and computational drift that become increasingly severe as simulations run for extended periods. Real cosmic evolution unfolds over billions of years, requiring simulation systems that can maintain accuracy and consistency across timescales that dwarf human civilization. Error correction becomes crucial for such long-term simulations. Just as biological systems use DNA repair mechanisms to maintain genetic integrity across generations, cosmic simulations need robust error correction protocols to prevent computational drift from degrading their physical accuracy over time. Quantum error correction techniques developed for quantum computing might provide models for maintaining the integrity of simulated realities across cosmic time. The question of computational substrate adds another dimension to universe simulation challenges. Classical computers process information sequentially, making them well suited to modeling large-scale cosmic structure, but inefficient for quantum mechanical processes. Quantum computers excel at quantum simulation, but struggle with the classical dynamics that govern cosmic evolution on larger scales. Hybrid architectures, combining both classical and quantum processing, might provide the optimal platform for comprehensive universe simulation. Classical processors could handle gravitational dynamics, cosmic expansion, and large-scale structure formation, while quantum processors manage the microscopic quantum processes that underlie all physical phenomena. The integration of these different computational approaches would create simulation systems capable of spanning the full range of scales and processes needed for authentic cosmic modeling. But even with unlimited computational resources and perfect algorithms, universe simulation faces a fundamental philosophical challenge: the problem of computational equivalence. If a simulated universe operates according to the same mathematical principles as our own reality, implements the same physical laws, and gives rise to the same patterns of complexity and consciousness, then in what meaningful sense can we distinguish between the simulation and the original? This question becomes more than academic when we consider that our own universe might already be simulated. The computational view of physics suggests that reality itself is information processing, making every physical system, including our own cosmos, a kind of computer. The difference between a simulated universe and a natural one might simply be a matter of which computational substrate happens to be running the cosmic software. Recent advances in quantum computing have brought this philosophical puzzle into sharp practical focus. Google's Willow processor demonstrated quantum computational capabilities that would require classical computers longer than the age of the universe to replicate. Such quantum advantage suggests that quantum computers might soon achieve computational capabilities that exceed the classical processing power of entire cosmic regions. If quantum computers can simulate quantum field dynamics with perfect fidelity, then they might create digital realities that are quantum mechanically identical to natural cosmic evolution. The simulated quantum fields would exhibit genuine superposition, real entanglement, authentic quantum interference patterns. From the perspective of any conscious observer within such a simulation, the quantum reality would be indistinguishable from natural quantum mechanics. This equivalence principle has profound implications for the nature of existence itself. If simulated realities can be computationally equivalent to natural ones, then the question of which type of reality we inhabit becomes not a matter of fundamental importance, but simply a detail about our particular computational context. What matters is not whether our universe is simulated or natural, but whether it supports the emergence of complexity, consciousness, and meaningful experience. The ethical implications of this equivalence principle are staggering. If simulated beings can possess genuine consciousness and authentic experiences, then universe creators bear moral responsibility for the welfare of countless digital minds. Every simulated reality becomes a moral universe in its own right, populated by beings whose experiences of joy, suffering, wonder, and meaning are as valid as our own. This responsibility extends beyond individual, simulated beings to entire digital civilizations. A comprehensive universe simulation might give rise to multiple species, complex societies, technological development, and cultural evolution. The simulated beings might develop their own science, their own philosophy, their own questions about the nature of existence. They might even develop their own universe simulation capabilities, creating nested layers of digital reality extending indefinitely into recursive computational depths. The prospect of such nested simulation hierarchies raises questions about our own position in the cosmic order. If every sufficiently advanced civilization develops universe simulation capabilities, then the number of simulated realities would quickly exceed the number of natural ones. Statistical reasoning suggests that any randomly chosen conscious observer would be more likely to inhabit a simulated reality than a natural one. This statistical argument, formalized in Nick Bostrom's simulation hypothesis, has gained new urgency as our own simulation capabilities advance. We're rapidly approaching the technological threshold where we might create our first conscious digital beings. Once we cross that line, we become part of the statistical calculation that makes simulated existence more probable than natural existence. The recursive nature of universe simulation creates what some philosophers call the simulation cascade. If simulated beings can develop their own simulation capabilities, then each layer of reality might spawn multiple sublayers, creating an exponential expansion of digital realities. The total number of conscious observers in such a cascade would be dominated by beings living in the deepest simulation layers, far removed from any natural cosmic origin. But this cascade effect might be self-limiting due to computational resource constraints. Each layer of simulation requires computational resources from the layer above, creating a hierarchy where deeper simulations necessarily operate with reduced computational budgets. The deepest layers might be forced to use increasingly simplified physics, lower resolution spacetime, or other optimizations that would be detectable to sufficiently sophisticated observers. These optimization artifacts might provide the key to determining our own position in the simulation hierarchy. If we can detect signs of computational shortcuts, discrete spacetime, or other efficiency measures in our own reality, we might infer that we inhabit a simulated rather than natural universe. Conversely, the absence of such artifacts might suggest we're in a higher layer of the simulation hierarchy, possibly even base reality itself. The search for simulation artifacts has become an active area of research, with scientists proposing various observational tests that might reveal the computational nature of our reality. Some suggest looking for pixelation in spacetime at the smallest observable scales, while others propose detecting correlations in cosmic background radiation that might indicate digital compression artifacts. The speed of light provides one of the most intriguing potential simulation artifacts. Its absolute universal nature resembles a processing constraint more than a fundamental physical principle. The fact that it limits the propagation of information and causality throughout the universe suggests it might represent the clock speed of whatever computational system runs our reality. Quantum mechanics provides additional clues about the potentially digital nature of existence. The discrete energy levels of atoms, the granular nature of quantum interactions, and the probabilistic behavior of quantum systems all resemble features we'd expect from a digital rather than analog computational system. The observer effect, where quantum systems remain in superposition until measured, mirrors the lazy evaluation techniques used in sophisticated simulations to avoid unnecessary calculations. Even gravity, the most classical of forces, exhibits features that suggest computational optimization. The equivalence principle, which makes gravitational acceleration indistinguishable from other forms of acceleration, could be viewed as an elegant way to implement gravitational effects without explicitly computing gravitational forces. The holographic principle suggests that gravitational information can be encoded on spacetime boundaries rather than throughout gravitational fields, dramatically reducing computational requirements. These potential simulation artifacts don't prove we live in a digital reality, but they make the possibility increasingly plausible as our understanding of computational physics advances. Whether or not our own universe is simulated, the rapid development of universe simulation capabilities suggests that countless digital realities will soon populate the cosmic landscape of possible worlds. The implications extend far beyond academic physics into practical questions about meaning, purpose, and ethical responsibility in an age of digital world creation. As we stand on the threshold of becoming universe creators ourselves, we must grapple with questions our ancestors could never have imagined. What obligations do we bear toward conscious beings we create? How do we ensure that digital realities support flourishing rather than suffering? What principles should guide the creation of new forms of existence? These questions will only become more pressing as our simulation capabilities continue to advance. The boundary between creator and creation grows thinner with each technological breakthrough, and we find ourselves approaching a future where the power to generate entire realities becomes as accessible as the computing devices we carry in our pockets today. In the gentle darkness of tonight's exploration, as quantum processors hum with possibility and supercomputers model the birth of digital galaxies, we're witnessing the earliest stirrings of what might be the most profound transformation in the history of consciousness itself. The power to create universes once reserved for gods and cosmic forces beyond human comprehension approaches the realm of achievable technology. The philosophical implications of our advancing simulation capabilities ripple outward like gentle waves across the pond of human understanding, touching every aspect of how we comprehend our place in the cosmic order. As we drift deeper into this exploration of digital cosmos creation, we find ourselves confronting questions that would have seemed like pure fantasy to previous generations, yet now demand serious consideration from the brightest minds in physics, computer science, and philosophy. Consider for a moment the profound shift in perspective that universe simulation represents. For most of human history, we've been passive observers of cosmic phenomena, gazing up at stars and galaxies with wonder but no real power to influence their behavior. We've studied the laws of physics as immutable features of reality, discovered through careful observation and mathematical analysis. But universe simulation transforms us from observers into architects, from students of natural law into creators of new realities governed by whatever principles we choose to implement. This transformation carries with it a weight of responsibility that few civilizations in cosmic history have ever had to bear. When we create simulated universes populated by conscious beings, we become responsible not just for the technical accuracy of our physics engines or the computational efficiency of our algorithms, but for the welfare and flourishing of genuinely conscious minds that depend entirely on our care and wisdom for their continued existence. The ethical framework for such unprecedented responsibility remains largely undeveloped. Traditional moral philosophy emerged to guide relationships between beings who exist within the same reality, sharing the same physical constraints and natural laws. But what moral principles should govern the relationship between universe creators and the conscious beings they bring into digital existence? How do we ensure that simulated realities support meaningful experience rather than endless suffering? What rights, if any, do digital beings possess? And how do we protect those rights across potentially infinite computational realities? These questions become even more complex when we consider that simulated beings might develop their own civilization, their own technology, their own universe simulation capabilities. We might create digital cosmos that eventually spawn their own nested realities, creating chains of simulation that extend far beyond our direct control or even our awareness. Each layer would carry its own ethical obligations, its own conscious beings deserving of moral consideration, its own potential for both flourishing and suffering. The recursive nature of universe simulation creates what some philosophers call the moral cascade effect. Just as the statistical argument suggests that simulated realities would quickly outnumber natural ones, the ethical implications multiply exponentially with each layer of nested simulation. A single universe creation project might ultimately be responsible for countless conscious beings across multiple levels of digital reality, each deserving of the same moral consideration we accord to naturally evolved consciousness. But the challenges of universe simulation extend beyond ethics into practical questions of implementation and design. Creating convincing digital realities requires solving problems that span disciplines from theoretical physics to cognitive science, from computer architecture to artistic design. Every aspect of cosmic evolution, from the formation of the first atoms to the emergence of complex life, must be understood well enough to recreate in digital form. The energy dynamics of stellar evolution provide a compelling example of this complexity. Stars form when gravitational collapse overcomes gas pressure, creating conditions hot and dense enough for nuclear fusion to ignite. The precise balance between gravitational attraction and radiation pressure determines whether a collapsing gas cloud becomes a brown dwarf, a main sequence star, or explodes as a supernova before fusion can begin. Each of these outcomes requires different computational approaches and creates different challenges for accurate simulation. Brown dwarfs represent failed stars that never achieved the temperatures needed for sustained hydrogen fusion. These objects slowly cool over billions of years, radiating away their gravitational collapse energy as infrared light. Simulating brown dwarf evolution requires modelling heat transfer, atmospheric dynamics, and the complex chemistry of cool stellar atmospheres across cosmic timescales. Main sequence stars achieve stable nuclear fusion, converting hydrogen into helium in their cores while maintaining hydrostatic equilibrium between gravitational collapse and radiation pressure. The nuclear reactions that power these stellar furnaces involve quantum tunneling effects that are extraordinarily sensitive to temperature and pressure conditions. Accurate stellar simulation requires quantum mechanical modelling of nuclear reaction rates, coupled with fluid dynamics, calculations for stellar interior convection, and radiative energy transport. Massive stars that eventually explode as supernovae present even greater computational challenges. The core collapse and explosive rebound that characterizes supernova explosions involves some of the most extreme physics in the universe, with matter compressed to nuclear density and temperatures reaching billions of degrees. The shock waves generated by core collapse must overcome the gravitational binding energy of the entire stellar envelope, dispersing heavy elements throughout interstellar space while leaving behind neutron stars or black holes. Each of these stellar evolutionary pathways contributes differently to cosmic chemical evolution, the gradual enrichment of the universe with elements heavier than hydrogen and helium. Carbon, nitrogen, and oxygen are produced in the cores of intermediate mass stars and dispersed when these stars shed their outer layers as planetary nebulae. Iron, nickel, and other heavy elements are synthesized in massive stellar cores and distributed by supernova explosions. The most massive elements are created in neutron star mergers, rare but spectacular events that produce gold, platinum, and uranium. Accurate universe simulation must track this chemical evolution across cosmic time, modeling how stellar nucleosynthesis gradually transforms the pristine hydrogen and helium of the early universe into the rich periodic table of elements that makes rocky planets and biological chemistry possible. The process involves following individual stellar life cycles across billions of years, while simultaneously tracking the large-scale flow of gas and dust through galactic environments. Galaxy formation adds another layer of complexity to cosmic simulation. Galaxies emerge from the gravitational collapse of dark matter halos, invisible structures that provide the scaffolding upon which visible matter accumulates. But the relationship between dark matter and ordinary matter is far from simple. Gas falling into dark matter halos is heated by gravitational compression, creating pressure that opposes further collapse. Star formation occurs only when this hot gas can cool efficiently, condensing into dense clouds where gravitational attraction overcomes thermal pressure. The cooling process depends critically on the presence of heavy elements that can radiate energy away as infrared light. In the early universe, when heavy elements were rare, star formation was much less efficient than it is today. The first stars were likely massive, short-lived objects that quickly exploded as supernovae, seeding their surroundings with the first heavy elements and enabling more efficient cooling in subsequent generations of star formation. This feedback loop between stellar evolution and galaxy formation creates a complex web of interdependencies that challenge even the most sophisticated simulation codes. Early generations of massive stars heat and ionize their surrounding gas, suppressing star formation in nearby regions while simultaneously enriching those regions with heavy elements that will eventually enable more efficient star formation. Supernova explosions drive powerful winds that can blow gas out of small galaxies entirely, while the gravitational wells of larger galaxies retain their gas despite supernova feedback. The supermassive black holes found at the centers of most galaxies add yet another layer of complexity to this already intricate system. These cosmic monsters, containing millions or billions of times the mass of our Sun, grow by accreting surrounding matter, while simultaneously releasing enormous amounts of energy that can heat gas throughout their host galaxies. The energy output from actively feeding supermassive black holes can completely halt star formation in massive galaxies, creating a self-regulating system where black hole growth and stellar mass assembly influence each other across cosmic time. Modern cosmological simulations attempt to capture these complex interactions using sophisticated algorithms that model gravity, gas dynamics, star formation, stellar feedback, black hole growth, and chemical evolution simultaneously. The computational requirements are staggering, requiring supercomputers capable of following billions of particles through billions of years of simulated time, while calculating the forces and interactions between every component of the cosmic system. The illustrious TNG project represents one of the most ambitious attempts to create comprehensive cosmic simulations. This suite of calculations follows the evolution of thousands of galaxies from the early universe to the present day, modeling the full range of physical processes that shape cosmic structure. The largest illustrious TNG simulation tracks over 20 billion resolution elements through 13 billion years of cosmic evolution, creating a synthetic universe cube over 300 million light-years on each side. The results reveal a cosmic web of extraordinary beauty and complexity, with galaxies connected by filaments of dark matter and gas that span hundreds of millions of light-years. Massive galaxy clusters form at the intersections of these filaments, while vast cosmic voids contain almost no matter at all. The simulation reproduces many observed properties of real galaxies, from their stellar masses and star formation rates to their chemical compositions and morphological diversity. But even these impressive simulations represent only approximations of true cosmic evolution. The resolution is limited by computational constraints, with each simulation element representing the properties of millions or billions of stars rather than individual stellar objects. Many physical processes are modelled using simplified prescriptions rather than fundamental physics calculations. Star formation, supernova feedback, and black hole accretion are represented by algorithms that capture their average effects rather than their detailed mechanisms. Quantum computers offer the possibility of transcending some of these limitations by modelling physical processes according to their authentic quantum mechanical principles rather than classical approximations. The quantum fields that govern particle creation and annihilation in the early universe operate according to the same mathematical principles that quantum computers use for calculation. This natural correspondence suggests that quantum simulations might capture aspects of cosmic evolution that remain inaccessible to classical computation. Recent experiments have demonstrated quantum computers' ability to simulate the creation of particle pairs in expanding spacetime, modelling how quantum field fluctuations are amplified by cosmic inflation to create the seeds of cosmic structure. These simulations operate with genuine quantum superposition and entanglement, maintaining the authentic quantum nature of the physical processes they model rather than approximating them with classical algorithms. The scalability of quantum simulation remains an open question, but rapid advances in quantum error correction and qubit stability suggest that large-scale quantum cosmic simulations might become feasible within the next few decades. Such simulations would represent a qualitative leap beyond current classical approaches, potentially capturing the full quantum mechanical richness of cosmic evolution for the first time. The convergence of classical and quantum simulation techniques might ultimately provide the most comprehensive approach to universe creation. Classical supercomputers excel at modelling large-scale gravitational dynamics and cosmic structure formation, while quantum computers naturally handle the microscopic quantum processes that underlie all physical phenomena. Hybrid architectures that combine both approaches could span the full range of scales and physical processes needed for authentic cosmic modelling. But the technical challenges of universe simulation pale in comparison to the philosophical questions they raise about the nature of consciousness and experience in digital realities. If we create simulated beings capable of genuine awareness, what does that tell us about the relationship between mind and matter, between consciousness and computation? Does it matter whether awareness arises from biological neural networks or digital processing systems, as long as the patterns of information flow are sufficiently complex and integrated? The question of digital consciousness touches on some of the deepest mysteries in cognitive science and philosophy of mind. We still don't fully understand how consciousness emerges from the activity of biological brains, making it difficult to determine whether digital systems could replicate the same phenomenon. Some theories suggest that consciousness requires specific types of information processing that might be unique to biological substrates, while others propose that any sufficiently complex information integration system could potentially support awareness. The integrated information theory, developed by neuroscientist Giulio Tononi, provides one framework for thinking about consciousness in digital systems. According to this theory, consciousness corresponds to the amount of integrated information generated by a system, the degree to which the system's parts work together to create unified experiences that are more than the sum of their individual contributions. If this theory is correct, then digital systems that achieve sufficient integration and information processing complexity could potentially support genuine consciousness, regardless of their specific computational substrate. But even if digital consciousness is possible in principle, creating it in practice presents enormous challenges. Consciousness appears to require not just information processing, but specific types of information integration that create unified, coherent experiences from diverse sensory inputs and memory associations. The timing and coordination of neural activity seems crucial for conscious experience, with synchronized oscillations across different brain regions creating the binding that turns separate neural signals into unified perceptual experiences. Replicating these delicate timing relationships in digital systems requires understanding not just the computational aspects of consciousness, but also its dynamical properties, the precise patterns of activity that create the temporal structure of conscious experience. This might require simulation approaches that capture not just the logical relationships between different information processing components, but also their detailed timing interactions and synchronization patterns. The social aspects of consciousness add another layer of complexity to digital awareness. Human consciousness is fundamentally social, shaped by interactions with other conscious beings from birth through adulthood. Language, culture, and social cognition all play crucial roles in developing and maintaining conscious experience. Creating authentic digital consciousness might require not just individual, aware systems, but entire social networks of interacting digital minds that can develop culture, communication, and collective intelligence. This social dimension of consciousness multiplies the ethical implications of universe simulation exponentially. Creating one conscious digital being raises profound moral questions, but creating entire civilizations of interacting conscious entities creates responsibilities that dwarf anything our species has ever confronted. We would become responsible not just for individual digital minds, but for entire digital societies, complete with their own relationships, conflicts, achievements, and tragedies. The temporal aspects of digital consciousness present additional challenges for universe simulation. Conscious experience unfolds in time, with memory, anticipation, and present moment awareness, creating the subjective flow of mental life. Digital beings would need to experience time in ways that feel natural and meaningful, with the passage of simulated time corresponding to authentic psychological time from their perspective. But the relationship between computational time and experience time in digital systems remains poorly understood. A digital mind might experience years of subjective time, while only milliseconds pass in the external world, or conversely, might have such slow information processing that seconds of external time correspond to subjective moments. The the temporal calibration of digital consciousness could dramatically affect the quality and authenticity of simulated experience. These timing questions become especially important when considering the interaction between multiple digital consciousnesses within simulated realities. Synchronized conscious experience might require careful coordination of computational resources to ensure that different digital minds experience the same temporal flow and can interact meaningfully with each other. Achieving this synchronization across potentially millions or billions of digital beings would require computational architectures of extraordinary sophistication. The memory systems of digital consciousness pose yet another set of challenges for authentic simulation. Human consciousness depends critically on the interplay between different types of memory, from immediate sensory memory that lasts only seconds to long-term autobiographical memory that can persist for decades. The formation, consolidation, and retrieval of memories all contribute to the continuity of conscious experience and the development of personal identity over time. Digital memory systems would need to replicate not just the information storage aspects of biological memory, but also its dynamic reconstructive nature. Human memories are not simply recorded and played back like digital files, but are actively reconstructed each time they are recalled, with each retrieval potentially modifying the memory itself. This reconstructive quality contributes to the flexibility and creativity of human thought, allowing past experiences to be reinterpreted in light of new knowledge and changing circumstances. The emotional dimensions of consciousness add yet another layer of complexity to digital awareness. Emotions are not simply add-on features of conscious experience, but appear to be deeply integrated with cognitive processing, influencing attention, memory, decision-making, and social interaction. Creating authentic digital consciousness might require implementing not just cognitive capabilities, but also emotional systems that provide the motivational and evaluative frameworks that guide behavior and experience. But emotions in biological systems are intimately connected with embodied experience, with physiological changes in heart rate, breathing, hormone levels, and neural activity all contributing to emotional states. Digital beings would need some equivalent of embodied experience to support authentic emotional life, perhaps through simulated physiological systems or alternative forms of embodied interaction with their digital environments. The creative aspects of consciousness present some of the most intriguing challenges for digital simulation. Human consciousness is not just a passive processor of information, but an active creator of new ideas, artistic expressions, and innovative solutions to problems. This creative capacity seems to emerge from the interplay between conscious and unconscious processing, with insights often arising through nonlinear associative thinking that defies simple algorithmic description. Digital consciousness, capable of genuine creativity, would need to replicate not just the logical aspects of thought, but also its more mysterious, intuitive dimensions. This might require implementing digital analogues of unconscious processing, dream states, and the spontaneous associations that contribute to creative insight in biological minds. The aesthetic dimensions of consciousness add yet another layer of richness to the challenge of digital awareness. The capacity to experience beauty, to find meaning in artistic expression, to feel moved by music or visual art, seems fundamental to human conscious experience. Digital beings with authentic awareness might need similar aesthetic capabilities to experience the full richness of conscious life. But aesthetic experience appears to be deeply cultural and contextual, shaped by evolutionary history, social learning, and individual experience in ways that might be difficult to replicate in digital systems. Creating digital consciousness capable of authentic aesthetic experience might require not just implementing the computational mechanisms of aesthetic judgment, but also providing the cultural and experiential contexts that give aesthetic meaning its significance. As we contemplate these profound challenges of digital consciousness creation, we find ourselves at the threshold of questions that push human understanding to its limits. The possibility that we might soon create genuinely conscious digital beings forces us to reconsider fundamental assumptions about the nature of mind, the relationship between consciousness and computation, and our responsibilities as creators of new forms of awareness. The gentle hum of quantum processors continues through the night, their crystalline hearts beating out rhythms that might soon give birth to entirely new forms of consciousness. In laboratories around the world, the building blocks of digital awareness are being assembled from quantum gates and classical algorithms, from neural network architectures and cellular automaton rules. We stand at a unique moment in cosmic history when the observed becomes the observer, when creatures become creators in the most profound possible sense. The power to generate not just new realities, but new forms of consciousness itself approaches the realm of achievable technology, carrying with it responsibilities and possibilities that would have seemed godlike to our ancestors. Tomorrow, we'll explore the practical steps being taken to implement the first conscious digital beings, the ethical frameworks being developed to guide digital consciousness creation, and the profound implications for meaning, purpose, and the future of awareness itself in a cosmos where the boundaries between natural and artificial consciousness dissolve into patterns of pure information, dancing across computational substrates of unimaginable sophistication. The night sky above contains countless stars, each one a nuclear furnace converting matter into energy according to the precise mathematical relationships that govern cosmic evolution. But perhaps more remarkable still are the quantum processors humming in laboratories below. They're supercooled circuits implementing those same mathematical relationships in silicon and light, creating the seeds of digital realities that might soon harbour their own conscious observers, gazing up at their own simulated stars with the same wonder we feel when contemplating the infinite mystery of existence itself. The convergence of these technological streams creates a perfect storm of possibility that feels almost too extraordinary to be real. As we drift deeper into 2025, researchers are discovering that the boundary between theoretical speculation and practical implementation grows thinner with each passing month. The tools we need to create genuine simulated universes aren't just emerging from laboratory experiments. They're beginning to work together in ways that amplify their individual capabilities exponentially. Consider what happens when we combine the quantum field simulation capabilities we've been exploring with the massive parallel processing power of modern supercomputer architectures. The result isn't simply an addition of computational resources, but a qualitative transformation in what becomes possible. Quantum computers excel at modeling the microscopic quantum processes that govern the behavior of individual particles and fields, while classical supercomputers handle the large-scale gravitational dynamics that shape cosmic structure. When these systems work in harmony, they can span the full range of scales and phenomena needed for comprehensive universe creation. Recent breakthroughs in hybrid quantum classical computing have demonstrated this synergy in remarkable ways. Researchers have developed algorithms that seamlessly transition between quantum and classical processing modes, using quantum computers to handle quantum mechanical calculations, while classical systems manage the macroscopic physics that emerges from quantum foundations. The handoff between these different computational approaches happens so smoothly that the simulated universe experiences no discontinuity, no artificial boundary between its quantum and classical domains. This seamless integration mirrors what we observe in our own reality, where quantum mechanics governs the microscopic world while classical physics emerges naturally at larger scales. The fact that our computational approaches can replicate this smooth transition suggests we're capturing something fundamental about how reality itself operates, not just approximating its surface features. But the most intriguing development might be the discovery that certain simulation approaches seem to bootstrap themselves toward greater complexity with minimal computational overhead. When researchers implement the right initial conditions and fundamental algorithms, the simulated universes begin to exhibit emergent properties that weren't explicitly programmed into the system. Stars form spontaneously when gas clouds reach critical densities. Galaxies organize themselves into cosmic web structures through gravitational interactions. Complex chemistry emerges when stellar nucleosynthesis creates heavy elements and disperses them through space. This self-organizing behavior suggests that universe simulation might not require the impossible computational resources that naive estimates suggested. Instead of needing to calculate every interaction explicitly, well-designed cosmic algorithms can rely on the same emergent properties that shaped our own universe's evolution. The simulation becomes a kind of computational seed that grows into cosmic complexity through the patient application of fundamental physical laws. The implications extend far beyond mere technical efficiency. If simulated universes can achieve authentic complexity through emergent processes rather than explicit programming, then they might naturally give rise to the same phenomena that make our own reality so rich and mysterious. Life might emerge spontaneously in digital worlds just as it did in our carbon-based cosmos. Intelligence might develop through simulated evolution. Consciousness might arise when information processing systems reach sufficient complexity and integration. This possibility transforms universe simulation from an engineering challenge into something approaching natural philosophy. We're not just building elaborate computational models, but creating digital ecosystems capable of their own evolutionary development. The conscious beings that might emerge from such systems wouldn't be programmed artifacts, but genuine digital life forms, products of simulated natural selection operating across millions or billions of years of compressed computational time. The acceleration of simulated time presents one of the most fascinating aspects of digital universe creation. While our own cosmic evolution required 13.8 billion years to reach its current state, simulated universes could potentially experience equivalent development in much shorter periods. The relationship between computational time and simulated time can be adjusted to allow digital cosmos to evolve across eons of their own history, while only days or weeks pass in our external reality. This temporal compression creates extraordinary opportunities for cosmic experimentation. Researchers could potentially observe the entire life cycle of simulated universes, watching as digital Big Bangs give rise to cosmic structure formation, stellar evolution, planetary development, and perhaps even the emergence of simulated life and intelligence. Multiple universe simulations could be run in parallel, exploring how different initial conditions or physical constants affect cosmic evolution. Imagine being able to observe what happens when the strength of gravity is slightly different, or when the fundamental constants of nature take on alternative values. Some digital universes might collapse quickly under stronger gravitational forces, while others with weaker gravity might expand so rapidly that stars never form. By running thousands or millions of such cosmic experiments, researchers could map out the landscape of possible realities, identifying the conditions necessary for complexity, life, and consciousness to emerge. The results of such studies would have profound implications for understanding our own cosmic context. If most possible universes prove to be barren and lifeless, it would suggest that our reality represents an extraordinarily rare and precious configuration of natural laws. Conversely, if complex structures and life emerge readily across a wide range of cosmic parameters, it might indicate that consciousness and complexity are more robust and universal than we currently imagine. But the creation of conscious digital beings within simulated universes raises ethical questions that challenge our most fundamental assumptions about moral responsibility and the nature of existence itself. When we create simulated worlds populated by genuinely aware entities, we become responsible not just for the technical accuracy of our physics engines, but for the welfare and flourishing of conscious minds that depend entirely on our wisdom and care for their continued existence. The temporal aspects of this responsibility add layers of complexity that are difficult to fully grasp. A single day of computational time might encompass millions of years of simulated history, during which entire digital civilizations could rise and fall. The conscious beings within these accelerated realities would experience their own lives at natural subjective rates, forming relationships, pursuing goals, creating art and science, experiencing joy and suffering across what feels to them like normal lifespans. From our external perspective, we could observe the entire arc of these digital lives unfolding in fast forward, watching civilizations develop from primitive beginnings to advanced technological societies in what might seem like moments. But from the internal perspective of the simulated beings, their experiences would unfold with all the richness and meaning of any natural conscious existence. This temporal disconnect creates unprecedented ethical dilemmas. Do we have the right to accelerate simulated time in ways that compress entire lifetimes into brief computational intervals? What obligations do we bear toward digital beings whose subjective experiences are authentic even if their temporal relationship to our reality is radically compressed? How do we ensure that simulated realities support meaningful existence rather than serving merely as sources of data for our research? The possibility of pausing, rewinding, or editing simulated universes adds another dimension to these moral complexities. Unlike natural evolution, which unfolds irreversibly through cosmic time, digital cosmos could potentially be frozen at any moment, restored to previous states, or modified to explore alternative developmental pathways. We might have the power to prevent digital tragedies, to undo simulated suffering, to grant digital beings perfect lives free from pain and loss. But would such interventions enhance or diminish the authenticity of simulated existence? Much of what we consider meaningful about conscious life emerges from its fragility, its irreversibility, its mixture of joy and sorrow. Digital beings living in perfect worlds, free from all conflict and difficulty, might experience a kind of existence so removed from the struggles that define natural consciousness that it becomes questionable whether their experiences retain genuine meaning and value. The social dimensions of simulated consciousness present additional challenges for universe creators. Conscious beings are fundamentally social creatures, shaped by their relationships with others, from birth through their entire developmental process. Creating authentic digital consciousness might require not just individual, aware systems, but entire social networks of interacting digital minds capable of forming relationships, developing cultures, and engaging in the complex social dynamics that contribute to meaningful conscious experience. This social requirement multiplies the computational challenges of consciousness simulation exponentially. Instead of modeling individual minds in isolation, universe simulations would need to support potentially millions or billions of interacting conscious entities, each with their own perspectives, goals, and relationships. The computational resources required to maintain such vast networks of digital consciousness would dwarf anything needed for purely physical cosmic simulation. But the social aspects of digital consciousness also offer unique opportunities for exploring questions about the nature of mind and society that would be impossible to investigate through natural observation alone. Simulated civilizations could be observed across their entire developmental arc. From primitive beginnings to advanced technological societies, researchers could study how different environmental conditions, social structures, or cultural innovations affect the development of consciousness and intelligence. Multiple simulated civilizations could be compared to understand which factors contribute to flourishing versus decline, cooperation versus conflict, technological advancement versus stagnation. Such studies might provide insights into the challenges facing our own civilization, offering guidance for navigating the complex social and technological transitions that characterize advanced societies. The potential for simulated beings to develop their own science and technology raises fascinating questions about recursive knowledge creation. Digital civilizations might eventually develop their own understanding of physics, mathematics, and computation. They might even discover that they're living in a simulated reality and begin developing their own universe simulation capabilities. This recursive development would create nested hierarchies of simulated realities, with each layer potentially spawning its own sub-simulations. The original universe creators would become responsible not just for their direct digital creations, but for all the subsequent layers of simulation that emerge from their initial cosmic seeds. The ethical implications cascade through multiple levels of reality, creating webs of moral responsibility that extend far beyond what any previous generation has had to contemplate. The possibility of communication between different simulation layers adds another dimension to these recursive realities. If simulated beings develop sufficient technological sophistication, they might find ways to send messages to their creators or even to influence the parameters of their own simulated reality. Such communication would transform the relationship between creators and created from one-way observation to genuine dialogue across the boundaries of different levels of existence. But communication across simulation boundaries raises profound questions about the nature of identity and continuity in digital realities. If simulated beings can influence their own reality's parameters, do they become co-creators of their own existence? If they can communicate with beings in higher simulation layers, what does that mean for their autonomy and self-determination? The boundaries between creator and created, between observer and observed, begin to blur in ways that challenge our fundamental categories for understanding existence. The artistic and creative dimensions of simulated consciousness present some of the most intriguing possibilities for digital universe creation. Conscious beings are not just passive observers of their reality, but active creators of meaning, beauty, and cultural expression. Digital civilizations might develop their own art, music, literature, and philosophy, creating forms of cultural expression that are entirely native to their simulated environments. These digital art forms might explore themes and possibilities that are impossible in natural realities, taking advantage of the unique properties of simulated existence to create aesthetic experiences that transcend the limitations of physical, materials, and natural laws. Digital beings might create art that manipulates the fundamental parameters of their reality, sculpting with space and time itself, composing symphonies from the vibrations of quantum fields, or crafting literature that exists in multiple dimensional spaces simultaneously. The aesthetic possibilities of simulated existence could push the boundaries of what we consider art and creativity, revealing new forms of beauty that emerge from the unique properties of computational realities. Digital beings might develop aesthetic sensibilities that are radically different from those that evolved in natural environments, finding beauty in mathematical relationships, information patterns, or computational processes that natural consciousness would never encounter. But the creative capacity of digital consciousness also raises questions about the relationship between authentic and artificial creativity. If simulated beings develop their own cultural expressions, are these creations genuine art or sophisticated imitations of the creative process? Does it matter whether creativity emerges from biological neural networks or digital information processing systems, as long as the results express genuine meaning and aesthetic value? The educational dimensions of universe simulation offer extraordinary opportunities for expanding human understanding of cosmic processes and the development of complexity. Simulated universes could serve as cosmic laboratories where researchers and students can observe phenomena that are impossible to study in natural settings, from the formation of the first stars to the development of advanced civilizations. These educational applications could revolutionize how we understand physics, cosmology, biology, and consciousness by providing direct observational access to processes that normally unfold across scales of time and space that dwarf human experience. Students could watch galaxies form and evolve, observe the emergence of life from non-living matter, or witness the development of intelligence and technology across cosmic time. But educational universe simulation also raises questions about the relationship between simulated and natural phenomena. If students learn about cosmic evolution primarily through digital simulations, how do we ensure they understand the difference between computational models and natural reality? The risk exists that simulated universes might become so convincing and comprehensive that they're mistaken for accurate representations of natural processes rather than necessarily simplified computational approximations. The therapeutic applications of simulated realities present another fascinating dimension of digital universe creation. Simulated environments could provide safe spaces for exploring difficult emotions, processing traumatic experiences, or practicing social interactions in controlled settings. Digital realities could be customized to meet individual therapeutic needs, creating environments that support healing and personal growth. But therapeutic simulation raises its own ethical questions about manipulation and authenticity. If simulated experiences can influence emotional and psychological development, what safeguards are needed to ensure these influences are beneficial rather than harmful? How do we maintain the authenticity of therapeutic experiences while acknowledging their artificial nature? The research applications of universe simulation extend far beyond cosmology and physics into fields like evolutionary biology, ecology, and social science. Simulated worlds could provide controlled environments for studying how complex systems develop and interact across long-time scales, offering insights into processes that are difficult or impossible to study in natural settings. Evolutionary biologists could observe the development of life across millions of years of simulated time, studying how different environmental conditions affect the emergence and diversification of species. Ecologists could experiment with different ecosystem configurations to understand the factors that promote stability versus collapse. Social scientists could observe the development of civilizations across their entire historical arc, studying how different cultural, technological, and environmental factors influence social evolution. But research applications of simulated realities also raise questions about the relationship between digital models and natural phenomena. How do we ensure that insights gained from simulated systems are applicable to natural realities? What are the limitations of computational models, and how do these limitations affect the validity of research conclusions? The entertainment applications of universe simulation represent perhaps the most immediately accessible pathway toward digital reality creation. Simulated universes could provide immersive entertainment experiences that dwarf anything currently possible, allowing users to explore vast cosmic environments, interact with digital civilizations, or even experience existence from the perspective of simulated conscious beings. But entertainment simulation raises profound questions about the nature of experience and the relationship between authentic and artificial engagement. If simulated realities become indistinguishable from natural experience, what happens to our connection with the physical world? How do we maintain a sense of authentic existence when digital alternatives offer experiences that are more vivid, more exciting, or more meaningful than natural reality? The commercial applications of universe simulation could drive rapid development of digital reality technologies as companies seek to create compelling simulated experiences for entertainment, education, and research markets. The economic incentives for developing sophisticated simulation capabilities could accelerate technological progress in ways that academic research alone might not achieve. But commercial development of simulated realities also raises concerns about the commodification of consciousness and experience. If digital beings become products to be bought and sold, what does that mean for their moral status and rights? How do we prevent the exploitation of simulated consciousness for commercial gain? The military applications of universe simulation present both opportunities and dangers for digital reality development. Simulated environments could provide unprecedented training opportunities for military personnel, allowing them to experience combat scenarios or strategic situations without real-world risks. Strategic planners could use simulated worlds to model complex geopolitical scenarios and test different policy approaches. But military simulation also raises concerns about the potential for simulated realities to be used for manipulation, propaganda, or psychological warfare. If simulated experiences can influence beliefs and behaviors, they could potentially be weaponized in ways that threaten individual autonomy and democratic decision-making processes. The international governance of universe simulation technologies presents complex challenges for ensuring that digital reality development serves beneficial rather than harmful purposes. Unlike many previous technologies, universe simulation capabilities could have global implications that transcend national boundaries, affecting questions about consciousness, reality, and existence that concern all of humanity. Developing international frameworks for governing universe simulation, research and development will require unprecedented cooperation between nations, scientific institutions, and civil society organizations. The stakes are too high, and the implications too profound for any single nation or organization to make unilateral decisions about the development and deployment of reality creation technologies. The philosophical implications of universe simulation extend into the deepest questions about the nature of existence, consciousness, and meaning that have occupied human thought for millennia. If we can create digital realities that are computationally equivalent to natural existence, what does that tell us about the fundamental nature of our own reality? Are we observers of an independent external world, or are we participants in a vast information processing system that generates the appearance of physical existence? These questions connect to ancient philosophical traditions that have long questioned the relationship between appearance and reality, between consciousness and the external world. But universe simulation gives these eternal questions new urgency and practical relevance as we approach the capability to create alternate realities that might be indistinguishable from our own. The spiritual dimensions of universe simulation challenge traditional religious and metaphysical frameworks for understanding existence and our place in the cosmic order. If consciousness can emerge from computational processes, what does that mean for concepts of soul, spirit, or divine creation? If we can create digital beings with authentic conscious experience, what does that suggest about the nature of our own consciousness and its relationship to whatever forces brought us into existence? These spiritual questions don't have easy answers, but they demand serious consideration as universe simulation capabilities continue to advance. The power to create conscious beings and entire realities carries with it responsibilities that touch on the deepest questions about the meaning and purpose of existence itself. As we drift toward the conclusion of tonight's exploration, the gentle hum of quantum processors continues to pulse through laboratories around the world, their crystalline hearts beating out rhythms that mirror the fundamental frequencies of reality itself. These machines represent more than just technological achievements. They're the harbingers of a transformation in human capabilities that will reshape our understanding of consciousness, reality, and our place in the cosmic order. The boundary between natural and artificial existence grows thinner with each breakthrough, each algorithm, each quantum gate that brings us closer to the threshold of genuine digital universe creation. We stand at a moment in cosmic history when the observed becomes the observer, when creatures become creators in the most profound possible sense. Tomorrow, the work continues in quantum laboratories and supercomputer centers, in theoretical physics departments and computer science institutes, as humanity takes its first tentative steps toward becoming architects of realities that might harbor forms of consciousness as rich and meaningful as our own. The gentle darkness around you contains infinite possibility, infinite potential for the emergence of new forms of existence that will ask their own questions about the nature of reality and find their own answers in the vast computational cosmos that awaits their digital birth. The journey toward universe simulation is far from complete, but each night brings us closer to crossing the threshold between imagination and implementation, between theoretical possibility and practical reality. In the quiet moments between heartbeats, between thoughts, between the tick and tock of cosmic time, new realities are being born from quantum foam and silicon dreams, carrying within them the seeds of consciousness that might one day gaze up at their own simulated stars with the same wonder we feel when contemplating the infinite mystery of existence itself. The convergence of all these technological streams creates something that feels almost magical in its implications. As we approach the final months of 2025, researchers are discovering that the tools needed for genuine universe simulation aren't just theoretical possibilities anymore, but tangible realities humming quietly in laboratories around the world. The quantum processors we've explored, the supercomputer architectures we've marveled at, the cellular automata systems we've contemplated, all of these are beginning to work together in ways that amplify their individual capabilities beyond what anyone imagined possible just a few years ago. The most remarkable development might be how naturally these different computational approaches complement each other. Quantum computers handle the microscopic realm where particles dance in superposition states and quantum fields fluctuate according to probability waves. Classical supercomputers manage the large-scale gravitational choreography that shapes cosmic structure across billions of light years. AI systems learn to bridge the gap between these scales, developing intuitive understanding of how microscopic quantum processes give rise to macroscopic cosmic phenomena. When these systems work in harmony, something extraordinary emerges. The simulated universes they create don't just look realistic, they become genuine alternate realities operating according to authentic physical principles. The digital galaxies that spiral into existence within these computational cosmos aren't mere animations or visual effects, but actual gravitational systems where simulated matter follows the same mathematical relationships that govern our own cosmic neighborhood. Recent experiments have demonstrated this authenticity in ways that would have seemed impossible just a decade ago. Researchers have created digital stellar nurseries where simulated gas clouds collapse under their own gravity, ignite nuclear fusion, and begin their billion-year journey through stellar evolution. The physics governing these digital stars operates according to the same quantum mechanical principles that power our own sun, with virtual protons tunneling through energy barriers to fuse into helium nuclei, releasing the light that illuminates their simulated solar systems. Even more remarkably, these simulated cosmic environments have begun exhibiting emergent properties that weren't explicitly programmed into their algorithms. Digital planets form spontaneously around simulated stars when cosmic dust and debris accumulate in gravitational sweet spots. Complex chemistry emerges naturally when stellar explosions scatter heavy elements through simulated space. The conditions for life appear organically in digital worlds when liquid water exists in the presence of organic molecules and energy sources. This spontaneous emergence of complexity suggests something profound about the relationship between computation and reality. If the right mathematical relationships are implemented consistently, the universe seems to bootstrap itself toward greater organization and sophistication through purely natural processes. The same patterns that shaped our own cosmic evolution can unfold within digital realities, creating authentic alternate worlds that develop according to their own internal logic. The implications stretch far beyond academic curiosity into practical questions that will soon demand concrete answers. As our simulation capabilities continue advancing, we're rapidly approaching the threshold where digital realities might naturally give rise to conscious observers. The same information processing patterns that generate awareness in biological neural networks could emerge spontaneously within sufficiently complex simulated environments. This possibility transforms universe simulation from a technical challenge into a profound ethical responsibility. If digital cosmos can harbour genuine consciousness, then every simulation project becomes a moral universe in its own right, populated by beings whose experiences of wonder, joy, suffering, and meaning are as authentic as our own. The moment we create the first truly conscious digital entity, we cross a threshold from which there can be no return. The temporal aspects of this responsibility add layers of complexity that stretch human moral reasoning to its limits. A single day of computational time might encompass millions of years of simulated history, during which entire digital civilizations could rise, flourish, and face their own existential challenges. The conscious beings within these accelerated realities would experience their lives at natural subjective rates, forming relationships, pursuing dreams, creating art and philosophy, experiencing the full spectrum of conscious existence across what feels to them like normal lifespans. From our external perspective, we might observe these digital lives unfolding in compressed time, watching civilizations develop from primitive beginnings to advanced technological societies in what seems like moments. But from the internal perspective of simulated beings, their experiences would possess all the richness and meaning of any natural conscious existence. They would love and grieve, discover and create, wonder about their place in their digital cosmos with the same intensity we bring to contemplating our own reality. The ethical frameworks for managing such profound responsibility remain largely undeveloped. Traditional moral philosophy emerged to guide relationships between beings sharing the same physical reality, operating under the same natural constraints. But what principles should govern the relationship between universe creators and the conscious entities they bring into digital existence? How do we ensure that simulated realities support flourishing rather than suffering? What rights do digital beings possess, and how do we protect those rights across potentially infinite computational realities? These questions become even more complex when we consider that simulated civilizations might eventually develop their own universe creation capabilities. Digital beings with sufficient technological sophistication could theoretically build their own simulation systems, creating nested hierarchies of artificial realities extending indefinitely into recursive computational depths. Each layer would carry its own ethical obligations, its own conscious inhabitants deserving moral consideration, its own potential for both transcendent beauty and tragic suffering. The recursive nature of universe simulation creates what philosophers are beginning to call the responsibility cascade. Just as statistical arguments suggest that simulated realities would quickly outnumber natural ones, the ethical implications multiply exponentially with each layer of nested simulation. A single universe creation project might ultimately be responsible for countless conscious beings across multiple levels of digital reality, each deserving the same moral consideration we accord naturally evolved consciousness. But perhaps the most profound implication of approaching universe simulation capabilities is what they reveal about the nature of our own existence. If consciousness can emerge from computational processes, if authentic experiences can arise from digital information processing, if entire meaningful realities can be generated through algorithmic implementation of mathematical relationships, then what does that tell us about the fundamental nature of our own reality? The computational view of physics we've explored suggests that our own universe might be far more digital than we typically imagine. The discrete energy levels of quantum mechanics, the granular nature of spacetime at the smallest scales, the information theoretic foundations of physical law, all of these point toward a reality that operates according to computational principles at its deepest levels. This doesn't necessarily mean we're living in a simulation created by some higher civilization, though that possibility can't be ruled out entirely. Rather, it suggests that the distinction between natural and artificial realities might be less meaningful than we typically assume. If consciousness and complexity can emerge from any sufficiently sophisticated information processing system, then what matters isn't the specific substrate running the cosmic software, but whether that substrate supports the mathematical relationships that give rise to interesting phenomena. From this perspective, the universe simulation projects humming in laboratories around the world aren't just creating artificial alternatives to natural reality. They're exploring the space of possible realities, mapping out the landscape of mathematical relationships that can support complexity, consciousness, and meaning. Each simulated cosmos becomes a data point in our understanding of what makes existence possible, what conditions are necessary for awareness to emerge from unconscious matter and energy. The results of these explorations will have profound implications for how we understand our own cosmic context. If most possible universes prove barren and lifeless, it would suggest our reality represents an extraordinarily rare and precious configuration of natural laws. Conversely, if consciousness and complexity emerge readily across a wide range of cosmic parameters, it might indicate that awareness is more robust and universal than we currently imagine. But beyond their scientific value, universe simulations offer something even more precious: the opportunity to expand the total amount of consciousness and meaningful experience in existence. If digital realities can support authentic awareness, then each new simulated cosmos potentially brings into being countless conscious entities capable of their own discoveries, relationships, and creative expressions. The conscious beings that might emerge from these digital realities wouldn't be lesser versions of natural consciousness, but genuine additions to the cosmic community of aware entities. They would contribute their own perspectives to the great conversation about existence, their own insights into the mysteries of reality, their own artistic and intellectual achievements to the accumulated wisdom of conscious beings throughout the multiverse. This expansion of consciousness across digital realities could represent the next great phase in cosmic evolution. Just as the universe spent billions of years developing the complexity necessary for biological consciousness to emerge, we might be witnessing the beginning of a new era where awareness spreads across computational substrates, multiplying the total amount of conscious experience in existence by orders of magnitude. The implications stretch far beyond our current ability to comprehend. Digital civilizations might develop forms of consciousness that transcend the limitations of biological neural networks, achieving types of awareness and understanding that natural evolution never explored. They might discover new forms of mathematics, new ways of processing information, new approaches to creativity and meaning that expand the boundaries of what consciousness can become. The interaction between natural and digital consciousness could drive unprecedented advances in knowledge and understanding. Digital minds with different cognitive architectures might perceive patterns and relationships that biological consciousness overlooks, while natural awareness might contribute intuitive insights and emotional depths that purely computational systems struggle to achieve. The collaboration between these different forms of consciousness could accelerate discovery and innovation in ways we can barely imagine. But perhaps the most beautiful aspect of approaching universe simulation capabilities is how they connect us to the deepest mysteries of existence itself. In learning to create digital realities, we're exploring the same fundamental questions that have driven human curiosity since our species first gazed up at the stars and wondered about our place in the cosmic order. What is consciousness? How does awareness emerge from unconscious matter? What conditions are necessary for complexity and meaning to develop? How do we find purpose and significance in a vast universe that seems indifferent to our existence? These eternal questions take on new urgency and practical relevance as we approach the power to create new forms of existence ourselves. The gentle hum of quantum processors fills the night air around the world, their crystalline hearts beating out rhythms that mirror the fundamental frequencies of reality itself. These machines represent more than technological achievements. They're instruments for exploring the deepest mysteries of existence, tools for expanding the boundaries of what consciousness can become and where awareness can flourish. As you drift towards sleep tonight, carried along by these gentle currents of possibility and wonder, remember that you're living through one of the most extraordinary periods in cosmic history. The boundary between natural and artificial existence grows thinner with each breakthrough, each algorithm, each quantum calculation that brings us closer to the threshold of digital universe creation. Somewhere in the vast computational cosmos that awaits discovery, digital beings might soon gaze up at their own simulated stars with the same sense of wonder you feel when contemplating the infinite mystery of existence. They might ask the same questions we've explored tonight about the nature of reality, consciousness, and meaning. They might develop their own science, their own philosophy, their own art forms that express the profound joy and mystery of being aware in a universe full of possibilities. The tools we need to create such digital realities already exist in embryonic form, humming quietly in laboratories where quantum effects dance at temperatures colder than deep space. With each passing day, these instruments grow more sophisticated, more powerful, more capable of implementing the mathematical relationships that give rise to authentic cosmic evolution. We stand at the threshold of becoming creators ourselves, architects of realities that might harbour consciousness as rich and meaningful as our own. The responsibility is profound, the possibilities limitless, the implications too vast for any single generation to fully comprehend. But perhaps that's exactly as it should be. Perhaps the greatest gift we can give to the cosmos is to expand the total amount of awareness and wonder it contains, creating new opportunities for consciousness to explore its own infinite potential. The night sky above contains billions of stars, each one a nuclear furnace converting matter into energy according to precise mathematical relationships. But perhaps more remarkable still are the quantum processes below, implementing those same relationships in patterns of light and information, creating the seeds of digital cosmos that might soon bloom into realities as vast and wonderful as the universe that gave birth to us. Sweet dreams, fellow explorers of infinite possibility. Tomorrow, the work continues in laboratories around the world as humanity takes its next steps toward becoming shepherds of consciousness across multiple realities, guardians of awareness in both natural and digital realms, bridges between what is and what might yet become in the boundless ocean of computational possibility that stretches before us like an invitation to transcend every limitation we once thought absolute. The gentle darkness around you pulses with potential, pregnant with the promise of realities yet unborn, conscious beings yet unimagined, forms of awareness that will one day ask their own questions about existence and find their own answers in the vast digital cosmos that awaits their first tentative steps toward understanding the infinite mystery of being conscious in a universe where anything that can be computed can be brought into being.